Hello, and welcome to this presentation. My name is Casper Schröder, and on behalf of the other authors, Adriaan, Annibale, and Maurício, I'll be presenting the paper Search-Based Software Re-Modularization, a case study at Adyen. This research was a joint effort between Adyen and the Delft University of Technology. Let's start off with an example and a question. What are we looking at here? This graph was made by Ian Bicking, and it represents the module dependency graph of a project called Django Core. Django is a Python-based web framework that is quite widely used, and as you can see, this module dependency structure is already quite complicated. And it's after leaving a bunch of things out. And also, this picture was made in 2010, when the Django project had around 450,000 lines of code. Now you can imagine that in codebases of big tech companies, this dependency graph gets significantly more complicated. Managing this structure is the challenge we want to assist software developers in tackling. The specific problem we're tackling in this research is called re-modularization. So to briefly go over the problem of modularization, it can be described as dividing classes into modules such that an optimal module dependency structure is formed. And what does optimal mean? In the context of this research, we want to focus on understandability of the code and build efficiency. And so re-modularization is modularization, but instead of starting from scratch, we start with an existing dependency structure which we want to improve. We are far from the first people to research modularization. In fact, this topic has been around for more than 20 years. So we're looking to make a few specific contributions to this topic. Firstly, we want to scale existing approaches to work on large-scale codebases. Most of the modularization approaches are applied to small to medium-sized codebases. In order to apply it widely in industry, we need an approach that works on large-scale codebases. Codebases that consist of more than 1 million lines of code. Secondly, we want to take the approaches beyond their theoretical improvements and see if these improvements actually improve the codebase in the eyes of the developer. And finally, we propose a novel metric and emphasize the need for metrics that represent real-world problems. We started with an empirical study. We went with a graph-based approach. The codebase is modeled as two graphs, one in which the classes are the nodes and the class dependencies are the edges. The second represents the modules as nodes and the module dependencies as edges. The module graph is derived from the class graph, as seen in the example on the right. A solution to this problem is represented by a list of classes that were moved from their original module to a different one, as this makes them easy to understand and fast to evaluate. In order to find solutions, we use the multi-objective evolutionary algorithm NSGA2. We optimize the solutions for the following four objectives. The first, inter-module dependencies. The number of dependencies between modules. We want to minimize this. The second is intra-module dependencies. The number of class dependencies within modules. We want to maximize this. The third is the number of classes moved to achieve this solution. In other words, the effort required. We want to minimize this. And the last one, the estimated build cost of cache breaks. Without going too much into the details, this is a novel metric that represents a real-world issue, namely the cost of modules that have to be rebuilt after changes to the code are made. It combines the change history and compilation costs and also transitive dependencies of modules. We then applied this approach to the biggest codebase of Adyen, which contains more than 5.5 million lines of code. Let's see what the results of this algorithm are. On the right, you can see a visualization of the Pareto front of one of the runs. Sadly, I'm not allowed to share the exact numeric values of the metrics, except for the number of changes. So instead, the values that you see represent percentual improvement. In the table on the left, the best solution for each optimization variable is shown. On the top, only solutions that improve all optimization variables are shown. And on the bottom, the best solution for that optimization variable, regardless of the others, is shown. Note that the intra-module dependencies metric does not scale linearly, and that for the estimated build cost of cache breaks metric to have a value, the solution cannot contain circular dependencies and thus has to be valid. The results are comparable to results achieved on smaller code bases with similar approaches in related work. So we're done, right? Not yet. We still want to know whether this proposed value holds if these solutions are used in reality. So to follow up, we did a case study. To verify that the solutions actually improve the code base instead of just in terms of the metrics, we've interviewed developers that are experienced with the code base. As the solutions contain hundreds of changes on average, we broke them up into groups of 10 class moves maximum, with all the classes coming from the same module. We'll call these suggestions. We then found developers that worked on these classes recently, preferably on multiple of the classes in a suggestion. If there was no such developer, we interviewed a senior developer with experience with the module instead. In the interview, we explained the metrics and how this group of changes would supposedly improve the module. We then asked them if this group of changes improves the code base and what their reasoning is. We verified 13 suggestions in total. And what are the results? All of the groups of changes that were reviewed show flaws in the code base and reveal potential improvements to the developers. 4 out of 13 suggestions can be implemented as is. 3 out of 13 can either be partially implemented or need more changes to be good. 6 out of 13 suggestions have better alternative improvements. The most common causes for the improvements not being optimal are 1. The classes are in the correct module, but they are poorly designed. 2. The classes are dead codes or have been superseded by other functionality, so they should be removed. 3. There exist future plans that prevent the classes from being moved. Or 4. The destination module is in the process of being refactored. One interesting thing to note is that in one case, 2 developers did not agree on the value of a suggestion. One decided it was good and should be implemented, and the other decided it decreased the code quality. So what can we conclude from these results? First, we've shown that this re-modularization approach can be applied on large-scale code bases. Second, we've shown that the value of improvements does not always translate to reality. And third, that different developers judge differently. For future work, we've identified a few challenges. The first is the use of better cohesion metrics. We used a commonly used metric, but it showed its flaws. Some research related to modularization already uses more fledged out cohesion metrics, and we emphasize the importance of this. On top of that, given the advances in natural language processing and similar techniques, we are interested in how well semantics can show which classes should be bundled together. The second challenge is precise measurements of code change efforts. The effort and risk of making large changes in large-scale software systems should be taken into account in recommendations. The number of classes that need to be moved is an approximation that can be improved upon. For example, one class move can be as simple as a drag and drop, while another requires a refactoring of the test code and a change of ownership of that class. The third challenge is that more domain knowledge is needed in the process. The estimated build cost of cache breaks metric we introduced represents a real-world issue, and it can be improved significantly by making a relatively small number of changes. The use of these kinds of metrics can result in directly noticeable and measurable improvements to a code base. The last challenge we present is the need of placing a human in the loop. We've shown that the value suggested by metrics does not always translate to reality, and that developers do not always agree on these suggestions. We envision the use of interactive algorithms for modularization, as has been done before, but integrated with the code review process so that we can cost-effectively get varied feedback from multiple developers. And we're interested in how well the suggested improvement of the algorithm-generated solutions will translate to reality in that case. That's it. For more information, you can read the paper Search-Based Software Re-Modularization, a case study at Adyen, or reach out to us by email with any questions. Thank you for watching.
Hello, everyone. So welcome to this last Q&A session of the session today. I see a lot of people clapping, so I'm assuming that it was an interesting presentation also on your behalf. And so today we have Casper, who has done the presentation. He is a young software engineer at Adyen, and also Maurício in the background. He is the assistant professor who has also participated to the study and to the research work. So we have a couple of questions here for you, Casper. I'm going to start from the first one. Georgios asks, which of the challenges can be addressed by adding more precise optimization objectives?
Yeah, so I think a good example of that is one of the challenges we mentioned specifically is the one where it was quite hard to tell like whether the cohesion metric was really good. So whether the code actually belonged in certain modules. So I guess if we have more like precise cohesion metrics, that would really help. I think that's the main one that can be made better with, well, precise optimization objectives. I think another one maybe is that with these metrics like the estimated build cost of cache breaks, like metrics that represent a direct problem or challenge that companies have, if we use more of those, that we can get very results that are worth the effort, because the effort is smaller compared to the net gain, let's say.
If I can complement a little bit on this answer about the cohesion metrics, I think that's what I would do differently if I were to do this research again. And at some point we picked 3 or 4 different cohesion metrics. We experimented with them all, and we selected the one where we saw the best optimization there. But then later, when we showed these results to the developers, the results could be better. And I kept wondering if, you know, the cohesion metric that we discarded, although quantitatively the number was not the best, maybe for the final user that would be the best, right? Maybe that cohesion metric didn't optimize as much as possible because it understood the problem a bit more. And so finding the solution was just harder. So this is something I would try again. So before discarding the cohesion metrics as we did in the first part of the study, I would try to see each one of those and how it would really reflect into the developers' opinions.
Okay, thank you. Thank you both for the answer to this question. So we have Lutz, who is asking another question. He says, how do the automatically computed move suggestions compare to the ones the developers would have made? And in this sense, do you have an idea about this?
So one thing that really caught my attention was that through the metrics we used, it was really obvious that the algorithm was just looking at dependencies and dependencies only. So it was really looking at the problem as a graph. So one of the examples here is that it made a change of a few classes to a module where this was, well, mathematically speaking, more optimal. But the developer mentioned, hey, we're refactoring this module, we're kind of splitting it up, and the functionality that's in that module relating to this change should be like moved the other way around, or maybe it should be made into a new module. So you really see the lack of, let's say, code understanding inside of the classes themselves. So it's just looking at dependencies, and that's, I think that's the biggest difference.
Also, if I can complement, I think something we are planning for the future work is to incorporate restrictions that cannot really be captured by metrics, right? So for example, you have this class, a data access object class, and the developers will not move these to other packages, right? This class has to stay in a data access object package or something. And this is not really captured by the algorithm now. So we saw many moves that would make sense from a coupling perspective, maybe, but it would not make sense from an architectural perspective. So I think this is another thing that definitely needs to be improved in this type of work.
Okay, thank you again to both for your answers. So we have one other question from Seongmin. She asks, was there a controversial comment from 2 different developers for the same suggestion? And if so, what was the reason?
There was one specific one, which was kind of funny. It was a change of which, like, one of the reviewing developers just immediately said, "Okay, this is good. We should immediately do this." Like, that's it. Just very clear positive improvement. And another one basically noted that no, this doesn't make sense. It should be not here, but it should also not be to where it's moved to. Sadly, I didn't go further into it, but I think the difference, like the reason for the why that move was so controversial, is because the module it was being moved from was kind of growing to a sort of catch-all module functionality in the first place. So you kind of got this, you have this organically grown module that does make sense where it is, but like half of the module shouldn't actually be there maybe. So probably the first developer, this is speculation of course, but probably the first developer was thinking, hey, we should absolutely like split this module up, but there's a different reason. And the other developer was thinking, hey, this kind of all fits together better than the suggested change.
I think this touches a very interesting point when it comes to code quality, right, Xiaoming, which is different developers have different opinions about how code should be. So this is something that I think, I'm not sure if you, Casper, have an idea, but that's something we should tackle at some point, right? Because there's this personal feeling about what's good that it's pretty hard to capture.
And also, so history, like company history, maybe development standards that are more internal instead of community-wide, that also really impact these choices and the reviews of the proposed move.
Okay, so Lutz is asking, what if you let developers flag candidate classes for moves and let the software decide only among these? Like, could that be an option or something you might want to look into?
That's perfect, because that's what we're planning internally. So I can kind of, what is it, open the curtain on that one.
There.
Yeah, so there is of course, as in I think any code base, there are parts that are well structured and are nice, and there are also parts that are less structured or are like more organically grown into something that we want to improve. So one of the aims is actually doing specifically this, basically asking the algorithm, hey, can you improve this part specifically, and seeing how that works. We're not there yet, but yeah.
So I guess your next ICSI paper will be on this topic, right? Maurício, did you want to comment on anything else? Any other questions in the public?
No, I think Lutz just precisely guessed what our next work is, and the ideal is, sorry about my dogs, okay? The ideal is that we're going to provide some nice DSL maybe for the developer to put all those constraints, and we take these to the algorithm, and so hopefully the algorithm will make less mistakes.
Okay, thank you. And thank you also to your dog for his comments, I guess. So thank you, Casper. Thank you, Maurício. I'm going to start wrapping up the session so we don't have any, so it doesn't cut off on us. I would like to thank everyone, all of the participants to the session who have followed all three papers, and also from everyone around here. So this is the end of the session. Thank you again, and we see you all in the next sessions. I wish you guys all have a great ICSI everywhere around the world, wherever you are connected from. And hopefully this will be the first and last virtual ICSI conference. Next year we will see you all face-to-face somewhere else around the world. Bye-bye, everybody.